Here we are. And sorry again for those who have joined. I'll just give a quick intro to Yaron. Um, Yaron is a serial entrepreneur, and we're very, very lucky to have him here today. He's been applying his deep technological experience in data, cloud, AI, and networking to leading startups and enterprise companies since the late 1990s. And as the co-founder and CTO of Iguazio, Yaron is drives the strategy for the company's data science platform. And I hope you do have a chance to check out the platform. You're going to have a chance to check it out throughout the next couple of days, as they will be on to demo that as well throughout the conference. So yeah, he drives the strategy for the company's data science platform and leads the shift towards real-time AI. He's also initiated and built Nuclio, a leading open source serverless platform with over 3,400 GitHub stars, and MLRun, Iguazio's open source MLOps orchestration framework. Prior to co-founding Iguazio in 2014, Yaron was the vice president of Datacenter solutions at Mellanox, which is now part of NVIDIA, where he led the technology innovation, software development, and solutions integrations. He was also the CTO and vice president of R&D at Voltaire, a high-performance computing, I/O, and networking company which floated on the New York Stock Exchange in 2017. And Yaron is an active contributor to the CNCF Working Group and was one of the foundation's first members. He presents at majority industry events and writes tech content for leading publications, including TheNewStack, Hackernoon, DZone, Towards Data Science, and more. I won't keep everybody waiting any longer. I'm very, very proud to announce Yaron, and I'll flip the mic over to him. I'm sure if you have any questions, you can pop them in the chat, and we'll take some time throughout the session to address those. Yaron, thank you so much. It's a privilege. Sorry to keep you waiting, and I hope you enjoy.
Okay, thanks. So really sorry for all the logistic issues and delays. So I'm Yaron, as you pointed out, and I'm CTO and co-founder for Iguazio. I'm going to speak mainly about MLOps and show how to build something which is more machine learning, operational machine learning pipelines. We'll go over the challenges. We'll go step by step. We have almost a couple of hours, so we'll go through demos. Everything I'm showing is also backed in the open source project that we mentioned, MLRun, with lots of tutorials and documents and notebooks. So you can also access the tutorial and the content later. And there'll be a way I can also forward more content, or you can touch base with me in LinkedIn or Twitter or any other social. And feel free to contact me in any of those channels. Also, there's a MLOps Live Slack channel. I can post the link in a minute, so people can also join that Slack and have discussion around MLOps related issues. It's with a bunch of different members from many different communities and leaders and heads of data scientists and practitioners. So without further ado, let's talk about some of the challenges when productizing machine learning and AI. And the base problem is that most of the projects today in machine learning start with the research environment in mind. That means that essentially people build a pipeline that has some, initially extracting data manually from different data sources that throw it into a notebook, a CSV file, a data lake, and so on. You run some data preparation, some training, you generate the model. In some cases, you even generate an endpoint from that model that serves reporting or some basic interactive applications. The main challenge is that if you really build machine learning applications that run as part of your business workflow, it looks more like the diagram on the right than it does the diagram on the left, which means that essentially we need to keep on feeding data from a variety of sources, ETL from operational databases, stream processing from Kafka or other event sources, integration with variety of APIs that add more information, more features into our model. Now we take all of those different data points, all of these features, we join them together, we process them at scale, we build aggregates, we build more insights from the raw content. This is usually done using batch tools. And then we feed that data set into a training job. That training job needs to run at scale. Unlike what we're doing in our laptop, in our notebooks, we need to be able to run a job across multiple containers and processes, multiple virtual machines at scale. maybe even run many different permutations of parameters and algorithms to choose the one that's most accurate or the best fit of our data. Once we generated the model, we have to go and generate the inference pipeline. It's usually doesn't end with a simple function that gets a request and responds. Usually there needs to be integration with APIs of the business application. It needs to access data, real-time data from operational sources. It needs to be monitored. You need to monitor accuracy, drift. Sometimes you build ensembles and more complex pipelines. And again, also integrating with APIs. So those pipelines that we see on the right are a lot more difficult to build. They have to be resilient. They have to work 24/7. They need to be able to absorb, version changes. You want to change a piece of code while the system is still running. This is not what you're doing in a lab, in a Jupyter. That's a different practice. In many organizations, it's actually a different team that builds the production pipeline. What we're going to try and see is how we can build a more continuous workflow for development, where instead of building something in the lab, throwing everything away and rebuilding it for production, we're trying to build a continuous workflow for development directly into production. And that's going to save a lot of engineering time and a lot of calendar time. What are the main challenges when we build something towards production or operationalizing it? So those are few major challenges. One is the fact that we work in silos. In most organizations, there's the data engineering part, which brings data, build the data engineering pipelines, and so on. We have the data scientists that work on the actual mathematical logic, building the models, training the models. We have DevOps or MLOps engineers, which take the work item from data engineers or data scientists and productize, make it work at scale, more resilient, more secure, in containers, in clusters, and so on. And each one of those people is working with a different set of tools. Some may work on Hadoop and Spark. Some other guys may work on Jupyter. A third guy may work on Kubernetes, on a cluster and containers. So essentially, we're refactoring everything over and over when we move from one silo to another, and we don't really have a continuous development workflow. The other part is that it's a very, very long process, and we're going to look into the individual steps within that process in a minute. It's a very long process to bring something into production. We need to think about packaging and testing and scaling it out and performance optimizations and securing of the data, handling versioning of the data, rolling upgrades, CI/CD, all those different acronyms. It goes down to the bottom line. It's a lot of time, a lot of people that need to work on making things operational. There are also major challenges in using data in production. So when you're training a model, you can just take CSV files that someone gathered for you and you run some training. Data may have been collected for a while from different departments, curated, cleaned, and so on, and then you work on it. But when you work in production, you have to serve model, you have to have exactly the same type of data that you had in the training. And sometimes you don't have access to that data, whether it's because of political reasons, security aspects, performance. Maybe it's easy to grab data over time, but now if you need in real time the same type of data, you can't just go and query your database over and over every time a user have a request. So those are major challenges of essentially accessing the same feature that we had in training, accessing them in production. And finally, one of the major challenges is maintaining the accuracy. So we may get some very nice accuracy when we're developing a model on test data, but as we go into production, because we're using slightly different features, potentially different engineering pipelines, may not have all the data and so on, our model accuracy drops. Maybe even the patterns of the data change over time. We trained on data from last year, and this year, fashion has changed. Maybe a virus like COVID came and changed the buying patterns of people, which translates to our model not being as effective as it was when we trained it on 5 years worth of historical data. So we need to always keep on monitoring our model, make sure that the accuracy is keep on being high. And if it doesn't, we need remediation plan, retraining on fresh data, building ensembles, and so on. So we need all of those different things. I don't have too much content on how to do all the math behind model monitoring. I can direct you later to separate webinars we did specifically on drift analysis and all the background around it. So these are some of the main challenges that we want to address. And again, it's very, very important to understand that you can't just take a notebook that you've written in the lab and say, you know what, I want to operationalize it. It doesn't perform, it's not highly available, it doesn't scale. So in many cases, you'll see that organizations, they take the notebooks and they refactor them. They rewrite them from scratch as a microservice. We're going to see what's a microservice, what's a container, and so on. But not just a microservice, they need to add telemetry and logging and monitoring and scaling and automation and CI/CD, all of that in order to, just like in software practices, build things that are sort of more sustainable and higher performance and more resilient. So this is the main thing that we need to do, is how to build something that is running in production and not just running in our notebook. You can't just take a project off of Kaggle and say, here I have a production pipeline. You need to do certain amount of work. Okay. Now, if we're looking into machine learning pipelines, there are essentially 3 separate pipelines, which are also being addressed by different people and in the organization. So we have the research pipeline, which is essentially grabbing offline data, usually from a data lake or maybe something smaller scale, doing some batch transformation, manipulating our features, our raw data into more meaningful and aggregated features, storing a snapshot of that training set in some offline storage, an object store, file store, a database, data warehouse, and so on, and training the model off of that part. Now, even training the model may initially be done using like notebooks and more interactive tools, but at a certain point, because we want to retrain the model periodically, we may want to train the model on a larger data set or more hyperparameter options, then machine learning engineers may take our notebooks and refactor them as a more of a distributed, dynamic, containerized workload. So this is just a research pipeline. The problem is that as we move into production pipelines, we have a totally separate pipeline, which is more real-time oriented, more online. So we don't tap into a data lake, we tap into operational data sources like Oracle databases, data warehouses, real-time logs that are pushed by our web servers, real-time streams coming from Kafka, and so on. So here the pipeline is quite different. It's not a batch pipeline where we just load some files. In some cases, it's actually sort of an ingestion pipeline with online transformation as the data flows in. We don't want to wait. We want to start manipulating the data as it flows in using stream processing technologies. Then, because we need quick access to the data, to the features, we usually store it on an online database, not as a very large file. And our serving is actually going and querying that online database and returning the value and so on. And this is not the done deal. Now we need to think about sort of the post-production, after we've served the models, what's going on. So we have to monitor all the models, all the activities, all the data that goes in, all the results that are going out of the model, to be able to do several things. One is measure the accuracy of our model, identify drift, identify performance problems, and so on. And also, for some legal reasons or compliance reasons, we have to be able to also explain the results of our model behaviors. Maybe it's doing some gender bias and someone is going to sue us and we need to be able to defend against it. So we have to have another analytical pipeline that grabs data from the serving, does the model monitoring in real time to identify problems, but also logs all the data for further analysis for explainability and so on. And this is a huge amount of work because we're essentially building 3 different pipelines that have nothing in common, with usually different types of tools, sometimes more performance-oriented or scale-oriented or more user-oriented, more for clickers or more for coders. So we find ourselves, again, investing a huge amount of resources, and we need to find a different way of building that in a more efficient and resource efficient way. Another main problem is the accuracy gap, because if we build different pipelines for research and deployment, we're going to generate different features, and different features means that there's going to be an accuracy skew. The accuracy of our training is not going to be the same as the accuracy of our serving, because we're not using the same data in both pipelines. So the project is now being more and more adopted, is to apply automation on two different parts. First is automation on the feature engineering and feature cataloging. A second is automation for all the other services that we've seen there, like training, serving, testing, monitoring, analysis, and so on. So the first part, which is very essential, is to put the data in sort of a data hub. Everything needs to go and be cataloged in one place. But it's not just the cataloging of the data, it's also the transformation pipelines, essentially the recipes for building the features from raw data, whether the raw data comes from files or databases or streaming or APIs. We also need the feature stores to be able to serve the data to different types of consumers. Could be training, so it's more of a batch, and we're going to look into that in a minute. So batch processing, or serving is more sort of real-time, very interactive, low latency, or even for monitoring, we need to be able to deliver the statistics of the features to conduct comparison between the real-time production data and the trained data, and also analysis tools that will analyze the production data, sort of the stored production data, to do all sorts of other analysis. And we want to use the concept of services or microservices on each one of those elements, so it will be easier to scale and productize and do versioning and so on. So this is the new architecture of more MLOps, where within MLOps there's also a concept of feature store, which is the cataloging and transformation element. We're going to demonstrate all of that and also dive deeper into it. So we mentioned that it's a very long process, anywhere from building some piece of code, whether this code is a training logic, a deep learning model, data engineering logic, data preparation logic, and so on. So we can test it locally with some sort of, again, notebook or other tools. But as we go into production, we have to go through all of those steps that you see here listed in this chart. So we have to take our code and package it. So again, refactor it into simple Python code with dependencies and packages and so on. In many cases, we handle lots of data, and we need to be able to scale out our workload. So for example, do load balancing, partition the data, partition the model, run AutoML to automate the different permutations of the execution, and so on. As we go into production, we don't want to waste too much computation or suffer from performance problems. So we need to tune the performance. Usually the code that is developed by a data scientist is not designed for performance, it's designed for functionality. So we may need to apply parallelism. We may need to apply, use GPUs to accelerate certain workloads, especially if it's deep learning. We may need to do caching for data and queries in order to be able to run maybe 100 times more transactions at the same infrastructure. We've seen projects where people develop something and it responded in like few requests per second, where the actual application was supposed to meet 1,000 or 2,000 requests per second to meet millions of potential users for that application. So you're not going to now buy 100 servers just to run more computation. If you write code efficiently, maybe you can essentially get 10x more performance without consuming more resources, just by optimizing the implementation. Other major things are instrumentation. As we go into production, we have to have full monitoring, see how much resources, how many resources are consumed, look at the logs. If something crashed, we want to be able to debug that. May want to version, development clusters, production clusters, rolling upgrades, and so on. And we must address security. So if our jobs are accessing data, we need to make sure they access the data with the right credentials and so on. And finally, we want to automate the entire flow. So every time we write a piece of code and load it in, we want some automation tools to take the code, build the production artifacts, deploy them into the cluster, and so on. And maybe even do A/B testing, test our deployment, see that it really works and it's great, and only then promote it to be the main implementation that's serving requests. So usually if you look into the productization efforts, developing a piece of code is relatively simple task done by a single guy, but productizing all those different tasks that we see on the scale take months of many people, data engineers, developers, DevOps people, data scientists, and so on. So what we want to do is try and minimize the effort of using automation tools, essentially be able to take a piece of code and productize it and add the scaling, the performance tuning, instrumentation, and so on without a lot of manual work. And this is really where MLOps comes into play. Okay, so before we dive into understanding how we address that, with the different open source tools, a few basic introductions. So first, I hope people are familiar with containers, but if you're not, this general idea is that you can take a piece of code with all the environment around it, environment variables, packages, operating system elements, etc., and put it in something called a container, which is like a software package, and you can just run it. And it's portable, and so you can go and develop it on your laptop and then run it on every execution engine. So in most cases, what you'll do in order to run your code in a production cluster is containerize it, okay? And use the Docker tools in order to containerize. And the next thing is usually you don't just run a container, you run a bunch of containers on a cluster. Something needs to schedule those container jobs on your cluster and define other requirements like how much CPU, how much memory is used. And this is where usually Kubernetes as the mainstream technology comes into play. It's essentially a cluster orchestrator where we can throw in definitions and it will run various tasks on the cluster. Again, it's open source, very popular, was originally developed by Google, but now is maintained by almost every vendor and cloud provider in this space. So the main challenge in Kubernetes is that every time you run something on Kubernetes, you have many manual things to do. This is like a pod manifest. It's sort of the base building block of building anything on Kubernetes. You need to give it a bunch of parameters, the containers, the execution environment, the packet, resources, and so on. And this is just the base building block. If you're building something more sophisticated, like a cluster of multiple containers, that will add complexity. If you need to add heartbeats and monitoring and so on, that adds more complexity. So many organizations still do that in the manual way. But what we want to introduce is a new concept of serverless. Some of you may have heard about Amazon Lambda and things like that. But the general idea is that instead of you creating the container and the Kubernetes definitions and all of that, you're providing some piece of software with some requirements, and that will automatically generate those containers and those dynamic functions for you. In many cases, if the serverless engines are smart enough, they know how to auto-scale, dynamically scale resources to meet the workload. They add logging, monitoring, security, and many other things in an automated fashion. So all those different tasks that we mentioned in this chart, all of those different things could be automated using serverless engines, which if they're done right. And this is really where part of the things that we're pushing for is the part of the way to operationalize machine learning faster is to leverage the concept of serverless engines, and we're going to see how it's work using a few examples. So another key challenge is that if you need to integrate all of those different things that we mentioned manually, you're going to end up with a lot of work, a lot of glue logic. Some things may work with a certain way of doing security and authentication, some other things a different way. Logging is done different on every tool. You need to learn all those tools. It's huge complexity. If you don't want to look like this guy, then one of the ideas that we have is essentially we've built a framework that automates all the processes around the main open source projects and look into a more automated stack with those different layers that you see here. So the underlying layer is the sort of data layer with an offline and an online feature store with data connectors to a variety of data sources like object store, like S3, NFS, or structured data stores. The next layer above is all those different serverless runtimes that know how to take a piece of code and operationalize it and scale it over a cluster. And in some cases, also take a pre-baked function. Like if you want to do training, you don't really need to write code if someone already built a training function for you. You can just pass parameters and reuse a market function, or essentially one guy in the team builds a function, another guy just imports it to his own project and runs it. And so this is sort of the underlying infrastructure. On top of it, you have different stacks or solutions for the different elements of the machine learning pipeline, the data ingestion preparation logic, the model training and testing pipelines, the real-time pipelines which gather data and sort of build models and more complex sort of graphs. And finally, the data and model monitoring to be able to see that our model behaves properly and also handle the remediation. And one other nice thing is that it's all layer is sort of has glueless management across all those different tiers, because there's one metadata sort of catalog for all the different objects. Security is done in the same way across all tools and so on, but it still works with all the different open source packages. So you can just go to MLRun.org and we'll see the documentation in a minute and see how it works, along with many different examples and installation instructions. So, and one of the, again, the philosophies around it is the sort of this serverless workflow, which is also continuous workflow. Instead of having one guy working on a notebook and then refactoring everything to production, we're looking into a more of a continuous development workflow, such that you go into your own IDE, whether it's a Jupyter notebook or a PyCharm or anything else, you load some SDK, you run locally. If you feel that the code is stable, debugged, with breakpoints, everything, you want to move to something bigger scale, maybe add GPUs or access more data and so on, you can just in a single command run it on a cluster. Once you have a piece of your pipeline working or a few pieces of your pipeline working, you could just assemble a pipeline, a graph or a DAG, directly a cyclic graph that shows the different steps that I want to run, and just launch the entire graph. For example, data preparation, and then doing training, and then doing some testing of the model results, and then sort of doing some deployment of the model and testing that this actually works, and so on. So you can build pipelines for development, but also you may need pipelines for the production, which are different. We're going to show what's the difference. Pipeline for production is, for example, grabbing real data from real data sources, doing real-time data engineering, doing model serving, more complex serving examples like ensembles and so on, and post-processing and so on. So we have either production pipelines or sort of training pipelines. And we also have all the telemetry that is being gathered. So if you do it right, then all the telemetry is automatically gathered. You don't need to add a lot of instrumentation or very little amount of instrumentation. And everything that you do will get monitored and logged automatically, so you can see what happened before. You can go to previous experiments and rerun them, or can see the production results. Another important thing is, in order to accelerate the productivity, you can actually build everything that you build could be sort of componentized. So you can build features and reuse them across projects, or you can build functions or models or any other object in the system and just store it as a template and reuse it anywhere else. I could tell you, I was speaking to one of our customers last week. I was telling me, okay, before we use your solution, it took us a year to productize something. The first few solutions, it took us, I think it was like in 90 days to produce few models. And after that, it sort of became less than a month that you're producing applications and models into production, because they started creating practices and templates. They don't redo everything. They just sort of, pass it through different data, a few different models, different production pipeline, and they have a new application up and running. So this ability to build components and then reuse them later is very powerful, as we'll see in a minute. Okay. Now, those serverless functions that we mentioned, they have several special attributes. They're not like traditional serverless functions. So first, you can take a piece of code and build a complete microservices around them using a single command line, as we'll see. They're very high performance. There's essentially built-in parallelism built into the runtimes of those serverless engines. So you, instead of making your code run slower, it will actually run your code faster as you migrate it into the serverless environments. Those serverless environments, unlike Amazon Lambda, etc., they're also stateful and distributed. So you can run a deep learning job or an analytic job across multiple virtual machines and multiple containers without modifying the code. The code is automatically being distributed using different parallelism techniques and low latency data sharing. So that allows you to scale to a very large degree without refactoring your code. And as we mentioned, we can build function marketplace and grab different functions from a marketplace and plug them into a running pipeline. So these are the general ideas beyond the serverless functions. The way that they work is that the piece of code that you have is essentially wrapped in some automation layer. And there are different types of what we call runtimes. Those are the things that execute your code. There's like Nuclio is for real-time jobs, and Spark is for people that sort of want to use like PySpark. Dask is like pandas, distributed pandas. Horvath is for deep learning, and so on. So there are different execution engines that master a certain workload, like distributed deep learning or distributed analytics could be done using different engines and know how to scale the workload in a very efficient way. Now, as we run the code in those automated and fully managed engines, we also pass parameters to the jobs and potentially security credentials. Let's say we want to access some database, we need the password. We want to pass it in a safe way. Some data pointers. And then when this job finishes the work, it generates results and operational data like logs, telemetry data like monitoring dashboards, artifacts, models, essentially sort of files or data sets that are being generated by this workflow. You may want to also plug those individual functions into a pipeline. So you need integration with some sort of pipeline mechanisms like Kubeflow or others. And another very nice outcome is that because there is a sandbox around everything that goes in and goes out into your job, then you get experiment tracking with very little amount of work. So everything you do will automatically get tracked because it's running within a sandbox. Okay. So, and you can read more information in the MLRun documentation slide. Okay, and as I mentioned before, every time you run, every function has an aspect of auto scaling and resource requirements and things like that. You can see here tolerations for sort of scaling. These are optional parameters. You can track everything that you're doing, every run, every version of every run. You can track the artifact that were used by or generated by every run. You could look into the telemetry data. And all of that without doing any additional work on your side. All of that is done automatically. Okay, so with that, let's look into some examples of how to build those functions and use them. Let's go here. So first, again, I recommend going to mlrun.org, and there are installation guidelines and also documentation. If you go into the documentation, you'll see almost everything I'm showing here is covered in the documentation. There's very basic demos and slightly more sophisticated tutorials and even variety how-to guides. One of which I'm gonna go over soon is taking the New York taxi demo from Kaggle and showing how to fully operationalize that. And there's also like real-time pipelines and feature store and so on. There's a lot of examples and content, and I'm going to share some of it with you now. So let's start with with a very basic function that we want to create. Functions don't have to be a training job. In a minute, we're going to see a training job and evaluation and building models. A function could just be a single task that we may want to do. Like this is a function that opens an archive, gets sort of the destination. You want to write the results of the archive and potentially get the archive URL, for example, something in S3. So we want to write a function. You see, it's just like a regular function. There's another something nice called context that could be injected. It's not mandatory. It could be injected into your function. And through that context object, you can get access to secret credentials. You can do logging of various artifacts and different things into your into the artifact repository or the experiment tracking mechanism. And you can also document your code, which is really recommended because that documentation is going to go into the actual user interface, as you'll see. So I can write a very simple piece of code which opens an archive, it does some logging, does some unzip, extract the zip into the destination. Notice that to pass data, we pass a Python object called data item. Again, it's not mandatory, but the data item object is a very smart object. It knows how to handle a variety of object store like S3 or Azure Blob Store seamlessly. So you don't need to go and download and integrate with like bot drivers for Amazon and so on. It has a lot of convenience features. It addresses security and credentials all in a sort of seamless way. Okay, so we have a simple function. In order to make that piece of code in our notebook a microservice, then we can just go and run something called code to function. And that will automatically analyze our notebook and create a microservice function. We can even add things like categories and labels and description, which will help us if it's essentially being pushed into the marketplace and we want to search by category or by label and so on. Everything that we create is essentially an object. So this object is creating some resource that it's translated by that Kubernetes cluster into something real. It's also, you can actually see that it recorded my docstring information and my APIs and so on, which will be used by the user interface and other tools. So as I built a function, I could just save it, or I can even export it into some place. And if I want to run a function, I can just import it, again, either from a marketplace or from a file. I can load the documentation, which essentially, seen all the docstring that I added here is essentially recorded with the function. And I could just create a task, which is what the parameters I want to use for my function. So I'm creating a task saying this is the name of the task. These are the parameters that I'm going to use, target directory where I want to place the images, and the archive that I want to, the zip file that I want to load. You can see it's actually an HTTP URL. So, but my function is not going to get an HTTP URL. It's actually going to get the data file because of this sort of data item object. And then I could just run this function with this task, or I could just place parameters with the flag of local equals true, meaning run this job on my notebook, and it will essentially run the job, track the results, and so on. The minute I want to run this on the cluster, it's just saying, just removing the local equals true. By default, it's local equals false. And this job is essentially going to run on the Kubernetes cluster. It's going to allocate those Kubernetes pods. But from my perspective, it actually looks exactly the same, whether it's running on the cluster or on my development environment. If I'm going to go into the MLRun project, it's this one. Okay, so this is the MLRun project that I'm logging all this information to. So this is my download function. I can actually see all the execution parameters, when it was ran, what were the inputs into that, what was the generated data, directory of images, logs for my execution, and so on. All of that happened without me doing anything. I just provided a piece of code, and I have something that just runs. Now, this is a batch job. Let's go into a scenario which is slightly more sophisticated. Let's go into a real-time scenario, and I'll show you it's actually simpler. Let's assume I want to build a function which has like a NLP function. I'm going to give it some text, and I want it to respond with sort of the sentiment or some translation of that thing. So I have a simple function called NLP, receives a text, some language, and prints the sort of the sentiment, the translation, and so on. Okay. It does depend on a package called TextClub. So if I want to run it locally, I need to install it. I'm just wrapping my function, and here I could just go and run this function locally. You see, I'm passing good morning. I want to translate it to Spanish, so I'm going to get the sort of the sentiment analysis along with the translation. Now let's assume I want to turn it into a real-time function that listens on an HTTP event. So again, same code to function. Just this time, I'm choosing a different runtime called Nuclio, which is a real-time, high-performance runtime, which allows you to support HTTP, Kafka, Kinesis, any streaming technology. I can give it some like baseline image that I need, and maybe some extra requirements, this TextClub package. And then the only thing I need to do is deploy. Deploy essentially does everything, builds the container for me with all the packages, adds instrumentation, security, everything. So then once my function is deployed, essentially it goes behind some HTTP endpoint, and I could just pass it some text and get back the results. So if I'm going to go into my project, this time it's in the real-time functions, I can actually go and see my code. You see it was auto-generated and is now stored in the Nuclio engine. And I could see the configurations of my function. I could choose scaling aspects. All those things could be now also from the SDK, but also from the UI. Package dependencies, volume, storage, secrets, everything which is operational could be done either through the API or through the UI. Right now, I chose an HTTP trigger, but I'm not really limited to HTTP trigger. I can actually make my function listen on a Kafka stream. And again, it will auto scale. It will handle the charting, the checkpointing. All those very heavyweight tasks are all fully automated for you. So with that, we've seen how we can write a very simple piece of Python code and operationalize it using a single line of code or CLI command, also support CLI. And again, you generated either a real-time workload or a batch workload, batch probably for the research or data preparation, real-time for things like serving or real-time data ingestion. Okay, so with that, let's move into, so there is a question, by the way, I'm running on Iguazio.com. So no, there's no dependencies on Iguazio platform. You can just download and run, just that Iguazio is a managed platform where all those services are fully managed, so you don't need to install anything. And it also comes with some other extra features around security, enterprise functionality, high performance data processing, and a few other things. And it runs, by the way, I see the question, it runs on premises or in any of the clouds as a managed service. But again, you're not required to install the production, the commercial product. You can also use the open source, and there's full description on how to install. On Kubernetes, there's a Helm chart. If you're a Kubernetes guy, there's essentially Helm chart of how to install. There's a Katekoda, sort of a tutorial, online tutorial of how to run the installation, and so on. The entire installation is like a few lines of code, and you're done. Okay. So all the other questions, paid, free, all that, you can maybe reach out to me later, and we can address all your points. Again, the key differences are first, you just get something that works on a managed with security logging, monitoring, integration with identity systems, LDAP and so on. And also another key strong point is the data access performance on the commercial product. But that's but in terms of functionality, most of the functionality not related to enterprise, grade stuff is in the open source. Okay, so going back into the presentation. So we've seen how we can essentially generate a function, real-time or batch, and just run it and get all the experiment tracking and all that automatically. Now, what happens when we build those machine learning pipeline is rarely a single task. Okay, it could be like running some exploratory data analysis, and then maybe some automated feature selection. Once you get the best features, you want to run some model training. And as you've done the model training, you may want to do evaluation and testing of that model. Make sure that it's accurate, make sure it performs in a decent way. So this is what we refer to as a model development pipeline. It's slightly different than a real-time pipeline. We're going to see what's a real-time pipeline in a minute. And that may differ. I've seen things that have like 20 or 30 different steps in a pipeline, because in some cases you need to grab data from multiple sources. You need some multiple data preparation steps. Sometimes you train multiple models. Even for the same application, you may have an NLP model and maybe a regression model all fit into the same application. And even testing could always get more and more sophisticated. Like maybe you want to do performance testing, maybe accuracy testing, maybe just test with many different types of data to see that your model is also resilient to attacks and so on. So, but this is in general the model development pipeline. And now remember, what we've done is we've componentized the different things. So each one of those things is a function. But between the function, we pass what we call tasks. Is essentially inputs, outputs, just chain them between one and the other. And we create graphs that run the entire thing. Now, because those are reusable functions, so we can build a training function and reuse it across all of our models. For example, we build a scikit-learn trainer or an XGBoost trainer or some other things, and we just reuse it. Or we can build other components for data preparation or feature analysis and reuse them. And in some cases, you don't even need to do that, because there is a function marketplace with like a few dozen functions that are pre-baked, and you can just load them into your pipeline. Now, as we build those pipelines, there are different tools that we may want to use. Some people may want to use tools that sort of on-premises or part of a, sort of like Kubeflow pipelines is something that we have packed in our service. Or some people use Jenkins. Or if you're in the cloud, there are like GitHub Actions or GitLab CI and different things that know how to run pipelines of different components. So this is an example of such a pipeline that first requires some deployment of different things, and then grabbing data, running training, deploying a model and testing the deployment in parallel to doing some feature analysis and potentially testing. So we want to be able to describe pipelines in an easy way. And one of the things that's very important when we do the tracking, we want the tracking not only to apply to what we're running on our notebook, we also want the tracking to apply to the workflows that we're running. So the same mechanism in MLRun, which tracks all the jobs and their results, etc., can also track an entire pipeline and even group. You can group by pipeline, group by task, and so on, compare by pipeline, by task. Another nice thing is using a glueless mechanism, you can also track all your results to other systems like TensorBoard. If you're using deep learning, it's very, very useful to just go and do the comparisons of epochs and all that in TensorBoard. Now, in those pipelines, every building block in the pipeline, there are some pipeline tools where all of that graph will actually run in a single container. That doesn't scale. Because we have the elastic function, so each step in MLRun could actually scale out to multiple containers. So you can handle enormous types of workloads. So this is that. And another interesting thing is you go and become more and more operational. You want to essentially integrate that within your CI system. So you want to, every time that you load a piece of code into a Git repository, for example, automatically run a certain workflow that validates the code or the model and so on, and throws the results of this pipeline back into your CI system, so you can go and see what was the impact of that pull request on the model accuracy, what were the data that have been used, and so on. So this is the general idea, is that we're not just focusing on individual step, but we can also work across multiple steps. Okay, so let's now look into a slightly more sophisticated example of building a pipeline. Let's take the okay. So one of the things here is an example of the full the New York taxi example. Is essentially it's in Kaggle. It's covered in the how-to guides here in MLRun. Essentially, what we wanted to do is take an example. Okay, there's a little noise. If you can mute.
But it is the best page in the world. We'll give it big PR.
If you can mute the microphone, please. Okay. So anyway, the New York Taxi Kaggle project is a very nice example of something that was designed for research. It's a single notebook that has everything in it, you know, the training, the testing, the data preparation, and so on. You can't really run it in production, but the application itself is sort of an online pipeline that gets information from taxis or users and provides them sort of real-time response. So what we wanted to show is how you take such a project from a notebook and turn it into something fully operational. So we've taken the example of the New York Taxi project with its own code. So this is same code which has data preparation aspects and also geolocation calculations and the training job, fetching data, training job. So this is sort of we didn't touch it. This is the original code, but now we want to convert it into like a production pipeline. So the only thing that we need to do is first create functions from the New York Taxi code. Give it some, for example, the images that we need, and like the default image in MLRun packs a bunch of useful tools. We want to run it as a job. We may need some extra packages like GPM and Shapely. We may want to just run this local. So we could just turn on the local flag and we run this job of data preparation locally, see all the artifacts. We can see that in the artifact monitoring as well. If we look into that object, a job has an object. So in the job object, we can look at the output and see, the data sets, the artifacts that were generated by that job. In order to run it on the cluster, we can, because we requested additional packages, we need to first sort of build our function using just deploy. This will essentially do like a Docker build and build all of the package dependencies for a function, and then just run the same function on the cluster. So you can see now that it's running on the cluster, it generated pods. Again, there's no difference between running in the notebook and running on the cluster. It's just one flag. You just remove the local equal true, and that now runs as a distributed job on the cluster. Now, after we've done the data preparation, we may want to do other jobs like the data transformation job, again, passing inputs. And we can also pass inputs from other jobs. So remember, we had the job that did data fetching. So we can pass the output of the data fetching as an input to the data transformation. Okay, and so on. We can do the same for training. We have a training function, again, passing the input, which was the output of the transformation, running, seeing all the results and so on. And then finally, we have a serving function. The serving function is real time, so it's using the real-time engine. And here, again, we are just creating a serving function. We're adding the model to the serving function, which is the output of the training. And we deploy, and we have a serving function up and running. So what we had is a 4-stage pipeline of bringing the data, running data transformation, running training, and then doing serving. All that is individual step. We debug each step individually. And now we build a complete pipeline. So in this complete pipeline, we use the Kubeflow pipeline for this case. I'll show in a minute how we can use other engines as well. So we want to essentially build a pipeline that builds our containers, run the ingestion job, the transformation job, the training job, and finally deploys the model. So all those different steps, we just want to create a graph, a DAG or a pipeline, where the inputs of one step, generating outputs, and then the outputs of this step is fed as an input to the next step, and so on. And we can build very complex topology. This is the most simplistic example. And then we could just run the entire, pipeline. We don't run this time a job.
Sanitizer then I guess.
Okay, we're running the entire pipeline. And if you go into the user interface of Kubeflow, you can actually see all those different steps of a pipeline. The pipeline. If you can mute, no one is unmuted, is not muted there. Okay, thanks. So again, we can build complex pipeline and just run the entire thing. If we go into the MLRun project, this is the New York taxi, we can see all those different steps. We can group by name or by workflow. We can see all the different versions of that run. And if we go inside, we can see the artifacts that were generated and so on. There are more sophisticated examples of, or for example, this is like a job with AutoML. So when we're running the training, in this case, we have the inputs, we have artifacts. So all the training was done automatically. This is using a library function that was doing the training, generating all the outputs, all the results from different permutations of our training, and automatically choosing the best result. So we can even automate further to add AutoML and hyperparameter tuning to our execution jobs. So this just shows how we can run the entire pipeline and see the results of the entire pipeline without essentially doing additional work, because building the function was something we did in the previous step. Here, the only additional step is building a pipeline and executing the entire pipeline. And that could also be periodically, like every time you need to retrain a model, you can just launch the pipeline. Another way to do it is using your CI system. In this case, it's GitLab, but it can also be GitHub or any other CI system. And I can build the pipeline directly as a script in my CI system. So every time something changes in my data preparation code, I want to essentially run the data preparation, run the training job using a library function which does scikit-learn training, a library function which does a model validation, creating the model serving function, and testing that the model serving function behaves according to what I need. So this is the complete script for fully automating our test and deployment of the machine learning workload. And every time that I'm going to modify the code, essentially what I'm going to see within my Git repository, in my pull request, in the request to change the code, I'm going to see the summary of all of the execution, all the pipeline, the different steps that ran in the pipeline, all the results, links to the data objects that were generated, hyperlinks to the jobs that I can open the UI and play with the data, etc. So this is how you can build a fully automated machine learning pipeline using relatively simple tools, and you don't need so many DevOps people and operation people. Just, again, very simple way of working through Python native environment, and in one command, translate it to something that runs on a distributed cluster at scale. Okay. So let's move to the next element. So one of the most difficult parts in machine learning is the first step usually in every project is the data preparation and collection. And what does it mean? It means that we need to take raw data from different sources, files, data warehouses, databases, HTTP, logs, streams, and so on. We need to run feature engineering on those different features to generate something more meaningful. And then once we have that more meaningful thing, we need to feed it into different machine learning applications. We need to feed it into training. So then it's sort of a batch access, give me a Parquet file or CSV with all the training set and run training and so on. We need to feed it into the serving pipeline. Again, so instead of having separate pipelines for training and serving, you can build one pipeline and just use it for training and serving. The only caveat here is that for serving, we need real-time access. We need low latency response. So, but it's the same data that needs to be accessed in different ways. And we also need to tie it into the governance layer, where essentially the governance layer will compare, analyze drift, analyze misbehavior in our data or our models in real time. So it does require knowledge of our features and the statistical behavior of our features, etc. And the features are the main thing that we need to have in our data science pipeline. These are the most important, most difficult pieces to handle. Okay, so and those are essentially, if you're building the production pipelines, you want to put this feature engineering as an automated flow. And also you will need to tie it into the production pipeline. So usually how the production pipelines would look like, you'll get some event from a user, from a stream, etc., requesting for some prediction. That will go through some APIs, and the APIs will do different transformations, extract data from a JSON and so on. Then we need to run through enrichment. So for example, we have a user ID, and we need to know if the user is a male or a female, its last location, how much he spent last year, and so on. So we need to provide enrichment of features. And then we need to pass that into the model serving layer. So that enriched set of features goes into the model serving. Some cases, we serve multiple models. We have short-term models, long-term models, and so on. But we need a combination, like an ensemble or other, or some weighted function of different models. And the result of them, the model serving will, on one end, go as an application response to the user. On the other end, will go into the governance layer and the monitoring layer. So all the data will feed into a monitoring system that will track if the model behaved, if we have some challenges, or maybe just for historical reasons to analyze why we give a certain prediction for a certain customer, and so on. So this is really how we build the online machine learning services. Again, the core component in building the machine learning pipelines for production is the feature engineering part. So what we want to do is build the transformation graphs, which explain how we take data from a source, a data warehouse, a stream, and so on, conduct a variety of transformations on that to turn it into a meaningful data set. And then that meaningful data set is persisted usually at least in two different ways, one for real-time access and one for batch access, like Parquet files for batch access and NoSQL implementation for real-time access. So we want to build the transformation pipelines. After we build transformation pipelines, we're starting to get our features into our system along with all their statistical behaviors, their metadata, their schema. All of that is learned automatically. And then as we build a project that needs features, we just go into that shared feature catalog in the feature store. We say we need those different features, create a vector, and let's use that vector now in different applications. Again, could be an offline training or data exploration application, or it could be a real-time serving application. So we want to use the same for different application. So, you may say that it's easy, relatively easy to go and get features to offline. You run some SQL queries, etc. Again, lots of work, but it's sort of doable. But building the production pipeline for real-time and stream processing, that's extremely difficult. That could easily take a few months of a bunch of people. But with the feature store, you're essentially getting that for free. You design your transformation pipeline once, and then you just load it as an online, as a real-time feature store, passing it an ID, and then just getting the result, the feature and rich features, and driving it into your model. Now, in those real-time production pipelines, again, you also have sort of a notion of a graph of different steps that feed each other. So an event arrives from a stream or an HTTP request. That event needs to go through enrichment, maybe some pre-processing, then potentially go to an ensemble, to multiple models that are being served, like random forest, logarithmic regression, etc., to choose the best results or sort of an average result, and then do some post-processing. Again, building the real-time pipeline is a huge engineering task. We want to show you that you can actually do the same thing with a few lines of code in Python, debug your real-time pipeline from within your native Python environment, PyCharm or Jupyter, put breakpoints, see everything is great. And the minute you want to run this entire real-time pipeline to production, you're one command away. Just say deploy, and it builds the containers, builds the deployments, distributes the containers on a cluster, monitors the containers, and so on, all that in a fully automated fashion. Okay. Now, it's not only the production pipelines that are being generated, but all the model monitoring, all the real-time telemetry is automatically attached to your workload without writing a single line of code. So every time I'm doing requests and getting the predictions after going through that pipeline we've seen before, which again integrates with the feature store, all the results from my serving function is logged into a real-time stream. And there are other functions that are sort of system functions that track that stream and analyze, compare the real-time performance, real-time behavior of the model serving with the historical data and the trained data set and so on. And based on that, provide some dashboards that show the behavior, the misbehavior of the model, the accuracy, the drift, and also may alert users if something happens, so we can retrain the model if we need to. So again, the model monitoring and tracking happens automatically as you deploy your serving functions. These are just examples of how we can actually see all the real-time model endpoints, the differences between production and real data and trained data, and also see everything in real-time Grafana dashboards in the open source version. So, okay, so, and in general, we can build a fully automated pipeline, which starts with, this is an example from healthcare application for real-time patient deterioration analysis. So grabbing data using the different function engines, whether it's a real-time, like Nuclio or Spark for batch, and so on, taking data into the feature store, running some exploratory data analysis on the collected features that are grabbed directly from production, running automated workflow for building the training, just as we've seen a minute ago. We can just plug this, machine learning training pipeline through an event that gets triggered from the, every time we need to train. This is generating the real-time functions that access the feature store for real-time features and enrichment. And all the results of that serving goes back through the model monitoring back into the feature store, so we can run analysis on the production features. So with that, we build a full automated pipeline from A to Z, all using the same set of tools and same automation, and everything here is reusable. Okay, so with that, let's move into sort of third and last demo. So let's look into that. Let's look into an application. This is an application for financial fraud analysis. I think it's also now in the demos. Here, if you go into the feature store, there are a few demos. There's a simple demo of stock analysis. There's a more sophisticated demo for the healthcare data. And I know we're adding the fraud example as well. But this is like covers the entire flow, as I mentioned, the data ingestion, the train validation, and the serving and monitoring, all in the same pipeline. So let's start with the data ingestion part. Okay, so the first thing I want to do is usually what we do, we set an environment to tell the system that it's using a certain project, so everything gets logged into a specific project. And so on. So the first thing we want to do is play around with the transaction data. So this is an example of fraud transactions with like merchants and and all of that you can see here. So what we want to do is create a feature set from that data. So what we can just do is create an object called the feature set, which is essentially a set of features that are ingested as a group. Give it a name, tell it what is my sort of key, what's the entity or entities in my data set. We see the source is essentially the key of the user making the transaction. So that's the entity. There's also a timestamp. You don't have to have a timestamp, but in transactional systems, you do have a timestamp. And give it a description. And now I'm essentially building a graph. My pipeline is doing data extraction from the stream and building aggregates, grouping data by time, doing aggregates by time, and the results are stored in offline and offline data, offline and online. So I'm building a graph that has data extraction for hours and days a week, windowed aggregates for average, summary, count, and maximum, with sort of a 1 hour period. And that's it, and I'm ingesting my pipeline. So I described a pipeline that can work in real time or in batch. Okay, so the same definition will work for production and for testing. And I can just go and I can run ingestion and test the results. So do you see already in your notebook, you can see how the results in the production pipeline would look like with aggregates, with some date. You see the date manipulations, date time manipulations. And now I built a sort of a real-time production pipeline for gathering data. Now we can also work on other data sets. We have an events data set that shows logins, logouts of those credit holders and other activities. So now we want to build another pipeline which has different transformations like one-hot encoding and value mappings and so on. So the new pipeline looks something like that: value mapping, one-hot encoding, and then aggregations. So again, we create a new feature set. We give it the categories for the one-hot encoding. We run the value mapping, the one-hot encoding, and aggregations. And now we have another feature set with sort of all of that data. So as a result. And finally, we may want to have the label data that actually tells us that we had fraud or we didn't have fraud as a binary field. So now we essentially created 3 different data sets: the transactions, the events, and the labels. And we want to go and train based on those. So relatively simple way to build production data pipeline. You've seen I just define each data pipeline. If I go into my project, you'll see that everything I did in the notebook is automatically logged. So I can look into okay, so remember I had the transactions. This is the source of the data. These are the features that were generated. These are the transformations I've defined in my notebook. Remember, this is the preview data, statistical behavior of each features in my feature set. this was all generated because I ran the notebook. That's it. And then I could use those features in production by just going to the featuring, creating a feature vector. So with that, I created the feature. Now I want to create the training set and run the training on that data. So again, defining which features I want from the feature store. So I want the transaction features with all the aggregates that we mentioned. We want the event features, all of them, and we want, there's also parties feature set, which is like grouping the operations of the credit card holder by transaction, like someone buying shoes or someone buying supermarket, it's different. Like you frequently go to the supermarket and buy stuff, but shoes, you rarely buy shoes unless you're my wife, but most of us rarely buy, especially if we're men, we rarely buy shoes. So an indication of someone buying more shoes, in the same week, that probably could be sort of indication of a fraud. So this is also why we have those parties and gender, etc., as things feed our feature vector. So we create a feature vector, and then we're just going to use it. So remember, we had features from different data sets that were ingested in different timing, and we want to join all those features into sort of a single vector that has time traveling. Essentially, everything is joined into the same time windows. So you can see all the different features from the different data that was ingested, the transaction data, the event data, and even the labels for those features. So by just collecting the features, just saying which features I need and collecting them, I now have a full training set. Let's import some function, MLRun function for scikit-learn classifier for AutoML, tell it which algorithms we want to run, and just launch this function. So as we launch the function, it's essentially running training, taking the feature vector, running training, selecting the best model for using AutoML, and provides, you see, nice accuracy, all the charts, feature importances and ROC curve, all of that was generated automatically. And we have a model that is stored. If we look at the run output, then it also has a model object that is used by our serving in a minute. Now we want to build the serving pipeline, essentially that gets an event, runs an ensemble using the 3 models that we built, and responds with the average of the ensemble. So with that, we can essentially go and build a model. We don't have to because that's a library function, but just you can see you can build a model serving function. It's using the standard sort of KF serving or Triton semantics. Essentially, every model server has like a load and a predict, but there could be some pre-processing and so on. In this model server, we have slightly more sophistication because it's also doing imputing for missing values in production. Let's assume that some of those aggregations, because we didn't have data during that time window, they're non-value, so we're not going to have the right results. We want to replace the non-value with some average value for that specific feature. So what we do during the load, we load the feature set and the feature vector. We also load the feature statistics from the feature vector. And during the pre-processing, we enrich, we essentially give it the source data, and it will automatically enrich our feature vector from the feature store. Now, we also want to do here some logic to replace nulls based on the statistical data stored with our feature store. So the feature store automatically stores standard deviations and averages and everything about every feature during the ingestion. So we can actually go and refer to those feature metadata, to that feature metadata, to prepare the data and do things like imputing. And then we run prediction based on the enriched data, and that's it. So that's building our model serving. But now we want to create a topology that uses our model serving. And here we're just going to go into the model database, run some query that provides us the different models, the 3 models that we created. And we just add those models into sort of a graph topology with an ensemble. Essentially, we created a function with an ensemble topology out of the box and just add the 3 models to it. So this is creating a real-time pipeline. Again, in the documentation, you'll see how things are done step by step. You don't need to remember everything I'm showing. If you go to serving and data pipelines, you'll see, from simple to harder examples. There is also like real-time NLP pipeline examples, and another example that will explain what I'm showing to you right now, sort of in a more step-by-step way. So I built a real-time pipeline. In order to simulate that my pipeline actually works, I'm building a mock server. It's a service simulator of the real-time pipeline. And here I'm taking the offline feature just to see that I can taking some of the offline data in order to test my model. Just to see that this thing works when I'm getting an offline feature for that vector. You see that I'm just simply feeding it with the key of the user, and I'm going to get the enriched vector that I defined previously. Remember, I defined information from the transactions, the event logs, and so on. Every time I'm feeding a user, I'll see all the information about that specific user enriched automatically. Now, I want to run it now through this real-time pipeline that I've defined. I can just test my virtual server, my sort of simulator server, infer on that model and provide the input, which is some ID of the user. And then I'm going to get the prediction, the output, essentially saying if it's a fraud or not, as sort of a 0 or 1. If I want to deploy that function to production after I tested, I've seen it's doing the right things. Only thing I need to do is say deploy. That builds a full production pipeline. And then I can test the production function using the invoke method, again, feeding it some data and getting back the results of the model. So that is a way to essentially build everything that I mentioned, all this operational pipeline. By the way, it's our organization. It could take a year to deploy this to production, what I just shown you. And here you can see that using those methodologies I've shown, you can, within a few weeks, you can get the full production pipeline with auto scaling, with security, with monitoring, with telemetry, with all those operational aspects that we've seen are done automatically for you. So yes, right, you can build some of those things by yourself using notebooks or some IDs, but then you have an army of people that build that to production. What you see here is that there's no army behind it. You build those things, and then they go into operational systems. Again, everything is monitored in production without adding a single line of code. I could just go and zoom into the model, see the feature behaviors in real time, all of that, drift analysis, accuracy analysis, all of that is built for you without any additional development over it. So, okay, let's go. Now I can show you another simpler example of how to build sort of a pipeline, just to show you that it's not as frightening. I'll do the simpler real-time pipeline, which has a very simple graph. So let's assume I have a few functions and classes that I just want to create like a real-time pipeline out of them. A function that does incrementation, ones that multiplies, maybe a function that have some state. Again, that this function I could just preserve some internal stuff, and every time I invoke that function, it will advance the counter. So let's assume I want to have this, and maybe build a graph that has, gets an event and then runs through those steps, step 1, 2, and 3. So in order to build that graph, it's actually not that hard. I have all those classes that you can write simple Python or use library classes that do more sophisticated manipulations. You do code to function to build a function off of that code with the processing engine called serving, maybe an image like Python 3.7. Maybe I want to install some extra things into it using pip. And in this case, I'm creating a special workflow topology. There are different topologies, but this is more like a graph topology. And here what I'm doing is essentially I'm saying, okay, I have 3 steps. One is using the increment function, one is the multiplier function, and one is using a class called withState. Remember, I have inc, mul, and the class withState. This will essentially automatically build a real-time pipeline that runs those 3 different functions and classes. So I can visualize that pipeline and see how it looks like. Essentially what it does, it preserves some, you see, it preserves some state machine and how it sort of combines itself. And then I could create a simulator and just ingest some data into the simulator and see the results. So, if you go back to the pipeline, add and multiply and so on, you'll see that's supposed to be the result. I'll run it again because I also had the state object with the counter. It'll say that generates additional results. And in order to deploy this into a production cluster, this pipeline, I can just go and say deploy, give it even a name if I want, and then invoke the stuff in production. Okay, so you see, you can build not only the training pipeline, but also very sophisticated real-time pipelines to production with relatively simple way of doing it without having to have, again, a lot of engineering to do that for you. Okay, and this is also, by the way, as I mentioned, there's some nice pipelines here as examples. This is a distributed NLP pipeline that shows how to take paragraphs, take documents, run some document processing on them, parsing paragraphs and so on, and then running entity extractions and enrichment, and finally writing the results of the enriched NLP into some output stream. So essentially you can take a bunch of sentences from a file and run this through the simulation pipeline, which will eventually produce enriched entity data. So you have those examples, and then again, to deploy it to production, you could just say deploy. This example, unlike the other ones, is using streaming. So it can tap on Kafka streams and generate the output into a stream and so on. So these are more streaming functions. But you can see here a lot of different examples, and it's a very broad system. It addresses deep learning, machine learning, NLP. It addresses the different steps of the pipelines as we discussed, or the data ingestion and preparation. We've seen the model training and testing automation. We've looked into the real-time data and model pipelines, and we looked into the monitoring. Everything built on one infrastructure where the underlying components are very, very scalable. You have the auto-scaling and the sort of fully managed experience driven by the serverless runtimes. And then all the data integration could also be optimized and automated for production at scale. So again, you can test what I've shown you in the notebooks, that you can test everything within a notebook and simulate and build your features. When you feel it's done, you just save it and use it in production. So the transfer, it's a more of a continuous development flow, or like CI/CD for machine learning, versus working in silos where one guy writes a notebook, throws it over the wall, someone else goes and refactors it. Every time you make a change in your notebook, you go and refactor it again. And then you sort of get tired of it at a certain point. This is more of a continuous workflow. You build something, you further optimize it, and you let automation build that into production, or you get collaboration. So maybe one guy is building a function for development, is not putting a lot of emphasis on performance or tuning or write packages and so on. He builds it into the pipeline. Someone else takes those individual functions and further tunes them without breaking the pipeline. Again, keeping the pipeline, just working on optimizing the various steps in the pipeline into better implementation of the function with more security, with more resiliency, better performance, and so on. So this allows you this collaboration we spoke about before, that different people can work on the same platform. Guys that want Spark can just run a Spark job. Guys that need notebooks, they can work against the system with notebooks. If you want to use Kubernetes at scale, again, system will build the Kubernetes resources for you and execute and monitor them. So you have one mechanism to go through the entire set of people and set of tasks that you have in your workflow. So again, I encourage everyone to just go over the documentation. I'll put some links here that you can see that. And now the MLRun project and other projects are now part of MLOps for Good hackathon. I recommend different people to so there is also the MLOps for Good hackathon, which is now being driven by our company together with Microsoft, MongoDB, and others. We encourage you guys to register. It's still not late. The idea is to do things for the sake of the society and good things. Go to the website. Sorry if you can, I see you shared the link. And what we really want to see in that hackathon is not the guy that built the best model. Is how to build things that go into production. How to take your model and put some life into it and build like a pipeline. Grabs data from some source, runs some computation and responds, with some activity. So we encourage everyone to go and join that hackathon. And there's also I'm doing a lot of sessions. There's also a live webinar series called MLOps Live. Sorry if you can share the invite link for the Slack also, and the link to the MLOps. So there's a lot of different YouTube recordings for many different topics. So we're interviewing people from Microsoft, GitHub, Amazon, NVIDIA, practitioners, the head of data science of a few different companies. Each one is talking about his experiences, his lesson learned, and so on. So we encourage you to go into the MLOps Live webinar series. I'll just look into. Let me share the link here. Oh, okay. I see, Sarah, you shared it. Yeah. So we have all those links. Again, encourage you to ask questions if you need more. If you want more knowledge, you can. If you go into the Slack channel for MLOps Live, then you can also call me out in the channel if you have specific questions. I'm more than happy to answer. Again, you can also reach me out in LinkedIn as well. So with that, let's see if we have any questions that I've sort of missed. Yeah, I've seen some question here around Cesar, you addressed it around Spark, Dask, etc. The nice thing about it, because of this separation of runtimes and functions and the sort of the pipelines and jobs, then you can build pipelines that comprise of many different components. The pipeline could start with data engineering on Spark or Dask. Can run some training on even external services like Azure ML or SageMaker, or containers on Kubernetes. Could go and build real-time function, as you've seen. So the pipelines could be very versatile and include different types of engines. We have very close collaboration with Amazon, Google, and Microsoft and their native tools. So you can also integrate it with like SageMaker, Azure ML, and so on. So I see there is a question, can MLRun be installed with Kubeflow? So MLRun itself is not part of the Kubeflow installation. It is some of the components in MLRun like Nuclio are mentioned in Kubeflow, but you just need to install the Helm chart, and it will talk to the Kubeflow. It knows how to detect Kubeflow, so you can install both separately. It's actually much easier to install MLRun than installing Kubeflow. And by the way, you don't have to use Kubeflow pipelines, because as you've seen, MLRun also has sort of a lightweight pipeline engine, which uses sort of a job to orchestrate the job. The pipeline is very good for like local testing. And then for bigger scale, you could use Kubeflow pipelines, or different CI tools, as I've shown before. So it works natively with Kubeflow. Again, it knows how to use Kubeflow as the orchestrator. Yeah, so I see a question around TensorRT. And so first, around jobs, you can execute everything you want in the MLRun runtimes, not just Python, by the way, any language, and the different runtimes. So Nuclio is the real-time runtime, but there's also like the job runtime, Spark runtime, etc. Each one handles the full orchestration, like the Spark runtime handle bringing up the master, the slaves, the execution engines, the jar deployment, all that automatically for you. So every runtime has its own specific deployment and execution and monitoring aspects. For TensorRT, then essentially you can also deploy TensorRT and work with the MLRun SDK, but we recommend using MLRun serving, which has the TensorRT API. It's essentially compatible with the TensorRT API, but it's auto-scaling. It has lots of capabilities. It has dynamic GPU scheduling, so it's actually better than TensorRT. It has native integration with storage, file volumes, etc., for storing your models. So it has the TensorRT sort of SDK and API, but it's a lot more automated and sophisticated. Also can listen on streams, which TensorRT cannot do. I see that. Regarding the Knative, so Knative, in my view, is not really serverless. Okay, I see that point. Serverless is when you've seen what I'm doing. I'm essentially putting a piece of code saying deploy, that's serverless. Knative means that you need to build a container and you need to build the sort of the YAML files and sort of all those things and then deploy it. It's a very, very basic serving engine, and it's very, very limited. Doesn't have stream processing, doesn't have auto scaling for things beyond HTTP, doesn't have fully managed experience like telemetry monitoring security like Nuclio. So we recommend using Nuclio. There are blogs, by the way, around there that compare Nuclio with Amazon, Lambda, and things like that, all in favor of Nuclio, because also the Nuclio engine has built-in parallelism, has multi-threading built into it. So Nuclio can do 60,000 TPS, essentially requests per second, on a single container, where Amazon Lambda does about 1,000. You mentioned OpenFast is probably like 1,000 or a couple of thousand events per second, where Nuclio does 60,000. To use binary code, it actually goes up to 400,000 events per second on a single process. Those are like phenomenal numbers. They would translate to cost reduction because people will actually need less containers to serve the same workload. We've seen anywhere at least 6 times cost reduction by customers that used it compared to other solutions. If you really want, you can use Knative in the pipeline, but that sort of defeats the purpose, because the way that Nuclio is integrated, you've seen it's all glueless. You just say launch, just say deploy, and it runs. Or you plug it in the pipeline as yet another step without any additional glue logic. So what's the difference between a feature store and a data warehouse or NoSQL database? So a feature store is not just the cataloging, it's not just the persistence of the data, it's also all the transformation pipelines. It describes how you build transformations. If you're doing a SQL thing, then you need to build SQL queries for each step of the pipeline. And also, SQL engine will not provide you the real-time serving part. You don't run SQL query every time you get an event from a user. You need other mechanisms which are more real-time, more NoSQL by nature. So a feature store provides you several things. It provides you the ability to build those transformation pipelines and persist it for real-time and batch processing, which you don't get from a data warehouse. The warehouse only does sort of batch processing and doesn't do the transformations. It provides you a cataloging service that you can just go and build your feature vectors, your feature set, collaborate. Every feature could have its own metadata. You could search features by owner, by labels, and so on. And then it has glueless integration with the training. Like, even if you work with the data warehouse, you need to provide the SQL query. Again, it doesn't work in production. And then the result needs to be persisted in some file, because you don't run the training directly off the database. Usually extract the data from a database, put it in a temporary location, and only then run it for training. Feature store does all of that for you. databases do not do statistical analysis on the data. So, and you need the statistical analysis for all those glueless model monitoring activities. So this data is actually feeding from the feature store metadata, which stores like standard deviations and histograms per feature for real time and offline. So again, feature store is essentially lots of automation for feature engineering. If you go into all the big companies, Uber, Netflix, Google, etc., they all have built a feature store internally for their machine learning teams. But most of you are not in the size of a Netflix, I assume, or Uber. So you want to leverage a commercial or an open source project like MLRun. So that's a question. So there are questions, what happens if tasks fail? So again, restarts, all that is built into them. That's really the difference between having some automated pipeline and just running one step at a time. We usually, another interesting thing in that framework is that we pass what we call data objects. So we don't really pass data, we pass pointers across the pipeline. Those pointers are versions. So if you're going to run the same experiment twice, essentially you're going to generate the data with different versions, and you could go into previous experiments and also see what was the data in the previous experiment along with the results. And let's see what other questions. So there's a question here about MLflow plus Seldon. So MLflow is really more of a tracking system. So if you think about MLflow, it's not about orchestration. MLflow is really about tracking. Every time you have to instrument your code, and then every time you run an execution, then you'll see the results of your code. Now, the problem is that you don't only want to track the result of your execution, and not to mention what happens, how do you apply MLflow to something that scales out beyond a single container? That's very hard. You also want to handle the provisioning. And what MLRun does, unlike sort of MLflow, is essentially takes what you want to do, it breaks it into components and orchestrates, build the containers, builds the manifests, the Kubernetes resources for you. Make sure it's all running automatically. If it doesn't, it does failover, it requires more resources, it will scale out and so on. So it's all the orchestration plus the tracking. So as you go into the system and you monitor the different tasks, you can actually see side by side those two things. So if I'm running a job, then it's also handled on one end, the scheduling of that job. You can actually put scheduled job and put a cron, etc. And as you run the job, you can also track it. And a lot of the metadata that's being added to the tracking is generated by the system itself. You don't need to log what computation would use, what packages were used, and so on. This is all automatically tracked because if you orchestrate the workload, you know exactly what were all the execution parameters. No one needs to tell you that. So that's one fundamental difference between MLflow and MLRun. MLRun does the full orchestration, builds pipelines, builds resources, and does the tracking of everything and model management and all of that for you. So it's both ends. The other question you had is with Seldon. So with Seldon, you can build some real-time pipelines, very limited. The Seldon API is very limited to, essentially you can pass like a vector of data. You can't pass binary data, like I've shown you an example of NLP processing. You cannot do that in Seldon. We have examples of image classification based on like binary streaming data, images and video streams. You cannot do those things in Seldon. And also in Seldon, all the DevOps have to be done by you. You build the containers, you build the YAML files, and then you deploy those things. I've shown you in those examples how I'm essentially taking a notebook and typing a single command, go to function, and I have a fully operational pipeline with multiple steps, something that will take a lot of work in things like Seldon. So in most of those frameworks, someone does the data science and then someone else refactors and does the ML engineering. And that's usually different people with a lot of manual work. You don't always see that because someone else is doing part of the work. What I've shown you, it is what it is. You're essentially typing a single command, you have a production system up and running. You don't have to pass it to someone else that will do the engineering and then do the deployment for you. So these are the fundamental differences. And also performance-wise, MLRun is significantly faster than things like Seldon because it's using the real-time processing engines that I mentioned with asynchronous processing and so on. So these are some major differences. Auto-scaling, stream processing, those things are not supported by most serving engines. By the way, the model monitoring, again, built into the system with the feature store integration is also very powerful. If you're using Seldon, you need to integrate it with the feature store. And what we showed you is that I didn't integrate anything. I just ran the serving and I got the tracking and drift analysis without doing anything extra, just by specifying to the serving function that it's using a specific vector. So that gives it all the information it needs to access the metadata and run the analysis in real time and do all that stuff. So the key thing that we're trying to do is essentially leverage automation and orchestration to speed up the way you're going to production. And again, we can see some testimonials of people using those tools. Some of them claim that it sort of speed their effort by at least 10x, 10 times faster time to production with a lot less resources. So you can translate it to less computation resources on the cloud, because again, all dynamic scheduling, auto scaling requires less resources on your Amazon bill. It translates to doing more projects with the same people. It translates, it's very hard to hire all those different personas, ML engineers, data scientists, and so on. If you manage to improve their efficiency, their productivity by magnitude, that's a huge advantage. And this is essentially what we're trying to do. Tools like MLflow and all that, they're really good only for the phase of building models and researching and experiment tracking. The problem is really you're going to get stuck. You're going to hit the wall the minute you're saying, okay, let's leave that experiment area and research area, and let's build a real application that taps into real data, does scoring, have to address security, have to address always on performance, scaling, and all of that. This is where most people hit the wall. And what I've shown you here today is really how to tackle that, how to pass that wall without putting tons of efforts and people into the problem. So that's in general. And again, don't feel free to talk to me over Slack or over LinkedIn. And again, love to keep on the conversation. So thanks, everyone. And with that,
okay, thank you so much, Yaron. I really appreciate it. And I hope everybody enjoyed that. Yeah, we'll look forward to seeing you and the team on the platform Wednesday and Thursday. And for those, again, who are joining the rest of the conference, tomorrow we have more workshops. Wednesday and Thursday will be on the Hopin platform, so you'll get a link to join that soon. Just to clarify, there's no need to register for individual sessions in the main talks on the 16th and 17th, just for the workshop sessions. So anyways, message your team if you have any issues. And as Yaron had mentioned, you'd also join in the MLOps community Slack channel, the group MLOps World. We're helping field any questions. Okay, so thank you so much, Sahara. Thank you, Yaron. Thank you for the team at Iguazio. I hope you enjoyed. Links and everything else will be sent post-event. We usually do a little bit of light editing. We'll collect some of the links that were sent and some of the files and so on that will help aid the presentation if you'd like to go back over this again. So I think that's it for me, and I will look forward to seeing you guys in some other sessions. Thank you so much. Hope you enjoy the rest of the day.